Hello, everyone. Thank you for coming. I'm Evgeny. I'm going to talk to you about how we are building in Fluence like a query layer for decentralized applications, why it's really needed and what it is and what's the impression how it works. So I would like to start with the example of meta search engine for airline tickets. And usually when we use Google Flights or Skyscanner or any other meta search engines, they work the same way. They aggregate airline tickets from many airline companies, they put it somewhere in their database, and then they allow you to search through these tickets in order to find the cheapest prices for your flight. And usually they have a user interface where you can specify city from to and many other parameters, and you see the search results. But what's problem with such services? Actually, they are not transparent for the user. I could give you some example. For example, one airline could probably pay Google Flights to exclude another airline from search results. So, and the user will never know that because it's all like a black box. This search happens on the server or the private company owned by Google. And it would be cool to create such a decentralized version of such Google Flights and have the all ticket prices open, transparent on a blockchain and allow you perform complex search requests across all of these ticket prices. But there are lots of challenges. There are prices are changing so often. The tickets, the high volume of data, we have high load from user traffic, and it's kind of should be really a real-time performant application in a browser. Traditionally, I probably should skip these slides. Traditionally, we use standard database solutions or data processing solutions. They all are they all works because they usually have an index. Index is a catalog of entry points to a data that allows you to find particular entries very fast and efficient, and that's in the traditional world that's fine and that works efficient. But this kind of leads us to centralized model when the whole search is performed on a server of particular company. So let's imagine that we are building a decentralized version of such meta search engine, and if we think about how it works, we just need to put all of the data to Ethereum blockchain, and then we have a browser code, a JavaScript that works in the browser that performs a search and takes data from the blockchain. And let's imagine that Ethereum solved all of these issues with scalability, so we could put everything on Ethereum and it will work fine. But actually, we do not connect to just Ethereum network. We connect our browser application to a particular node that either it's in Fury infrastructure or either Scan or Miser wallet or whatever, or you create your private node. And the problem here is your user that runs the code, the JavaScript in the browser, have to trust this node. Have to trust that this node responded correctly and the results was really honest. And also, if we do not pay to a node provider, we don't have any guarantees for SLA. Nobody guarantees us that this node that we connected will be online in the next few seconds. So that's kind of problem. And another issue here, if you don't like my example with meta search engine, imagine that you would like to display in a browser history of token balances of particular address. And to do this, you actually need to do a lot of requests to Ethereum node. And this creates kind of poor user experience for the user because everything works slow. It's not it's really slow and really bad performance. And we still need to trust our node that we connected to. And the usual solution for this is, okay, let's have our own server, let's install database that we like, it will have index that we need, and we will be able to perform queries or requests that we need for our application. But the problem here is our user still needs to trust this server. Our users still need to trust our private infrastructure that connected to Ethereum network. And this is kind of not a decentralized spirit. So finally, we have the problem that user needs to trust the node provider, either it's third-party node provider or it's like us, our node. We don't have any flexible query language to perform a complex search request, like with different parameters and so on. And we basically have really slow UX and like no SLA until we pay for it. Can we do this better? Probably yes. Let's imagine that we just replace this particular node to a network of nodes that connected to each other. They replicated our like database with index, and so we will be able to perform the queries that we need by requesting these nodes, and they will be able to prove somehow that this response was correct. That would be really cool, though. We will need less trust from the user using such network. And we will not be limited just a Ethereum data. It could be like we could use such an indexing network to get data from any data sources from many other blockchains, decentralized file storages, centralized file storages, any kind of data sources. Or even we could just put data directly from a browser, from one client, and read by another client. And also, it would be really cool if we will not be limited by just one query language or data interface. It would be cool to have like SQL, GraphQL, and NoSQL, and any other custom interfaces that we need. Having such a network, we will need less trust. We will have flexible query languages. We will be able to create really real-time applications in the browser, and they will be more decentralized than when you connect to a single node. And that's actually what we are building in Fluence. And Fluence is a decentralized data infrastructure that based on independent network of nodes that provide that highly optimized for real-time use cases, for real-time performance for the end users. And and actually Fluence highly optimized for real-time performance. It's fully trustless. So in order to use the network, user don't have to trust the node that it connected to, because all of the queries are verifiable, and I will talk about it a little bit later. It works with many query languages, and actually very simple diagram. We have hardware owners who provide the resources for the network and could monetize this hardware by participating on the network and store the data and perform the data operations and respond to requests from users. They could earn tokens for that. We have developers who could implement their own query or data interfaces or data structures or query languages and upload it to a network. And we have users who actually use applications in the browsers that could connect to a network and get a really real-time user experience. And few words how it works inside. For this, in order to optimize the network for really great performance, we organize nodes to clusters. Cluster is a relatively it's few nodes, relatively small amount of nodes that well connected. They replicate. They, for example, are responsible for a particular data set, and they have fully replicated data inside the cluster. And clients connect to this cluster in order to read data or do queries and write data and so on. And we have the verification nodes who are perform the what we call it batch verification for the queries, and I'll talk to it a little bit. So the essential thing here is in order to create such a network, we need to have a way to verify queries. We need to have a way for nodes to prove that the response that they provide is correct. So how could it be done? At first, of course, we have the consensus inside the cluster. So we need a majority of the nodes to agree on the results of the query. And beside that, if a client does a request to a cluster onto a particular node, it has a response with the Merkle proof of response. And Merkle proof is basically a structure that allows the client to verify this response was correct. And if a client have an access to a root chain where the root state of the whole database is stored, it could verify the response without any other confirmations from other nodes from the network. So the client have a few ways to verify a request. First is to verify Merkle proof with root state of the database. And second is to wait until more confirmations from a network from other nodes from this particular cluster. And second thing, if a client needs more security, we have the huge amount of verification nodes who verifies requests that was performed by a cluster in a little bit a delayed mode. So they, in certain period of time, they verify the queries in very similar, using similar mechanism as I explained in one slide before, and they sign that this request was performed correctly or incorrectly. If the request was incorrectly, the cluster is being removed. And of course, in order to have the honest behavior on the network, we have the security deposit. So in order to store some data on the network, you have to create a smart contract between you and the node or in the cluster, and a client and the cluster have to put some security deposits on that. And if the network is sees that this request was not performed correctly, or this data is disappeared, so we have an insurance for both parties that they will get their money back. And also it's important for nodes because they perform a work, and it also guarantees that the client will pay for the work that was performed correctly. And finally, if we build such a decentralized meta search engine, we would probably use Ethereum for the financial transfers, and we will need the Fluence for data queries and search requests and performing the computations on top of data that needs to be displayed in the browser in a second or just momentarily. And I could show you a quick demo. It's better to show it here in a browser. Yeah, so let's try. What I'm doing now, it's kind of could be problems with Wi-Fi, so I'll try again. I'm generating keys, just key pair to connect to a network. And yeah, now I'm connected, so it's a private test network. It's a small node that operates only by us. And now what I did, I opened the web page. It has a JavaScript, and I connected directly to a network. like without any trusted nodes, but these nodes, of course, operated by us, but it's temporary. It could be like any nodes. And we have the first implementation of key value interface with range requests, and we have the data is organized in Merkle B trees on the nodes. So when we do requests, when we put data or get data from a network, we receive Merkle proof that this part of data was put in a particular place of Merkle B tree. So let's try to read something here. Probably, yeah, I could not read anything now because this key pair that I generated was new, and this contract, storage contract, is just created. So, but I could put something like some data there. Like, let's put just a few strings. Oh, seems like the connection is not so good. Still trying to get a response. Oh. Probably I could do again. It just like, I don't know, the Wi-Fi always on the conferences is a kind of challenge.